Mercury became reachable only after mission planners agreed to let another planet decide where their spacecraft would go. NASA's Mariner 10 mission would become the first mission in history to use a planetary gravity assist to reach another world. The idea was tied to a mathematical proposal associated with the Italian scientist Giuseppe Colombo. If the prediction proved wrong, the mission's primary objective could disappear into deep space. The contradiction sat quietly inside a line drawn on paper. How did an untested mathematical idea become the key that unlocked Mercury? Mercury looks close. On diagrams of the solar system, it circles the Sun far inside Earth's orbit, appearing almost within reach. The visual impression is deceptive. Mission planners studying routes to Mercury discovered that distance was not the real problem. The problem was motion. Mercury races around the Sun at tremendous speed. Any spacecraft leaving Earth does not simply travel inward. It must reshape its own path through the Sun's gravity, matching conditions that are very different from those surrounding Earth. On orbit maps, the difficulty becomes visible. Lines that seem short become expensive. Trajectories that appear direct become impractical. Reaching Mercury begins to look less like crossing a gap and more like solving a puzzle. The first options to disappear are the simplest ones. A straightforward route demands mission architectures that quickly become unattractive. Fuel is limited. Launch capability is limited. The closer planners examine the problem, the smaller the collection of realistic paths becomes. Mercury remains on the map, but the routes leading to it begin to vanish. And as familiar solutions fade, another line starts to appear. It is not a spacecraft. It is not a launch vehicle. It is a sketch. On paper, a trajectory curves away from Earth, passes Venus, and then reaches Mercury. The drawing suggests something counterintuitive. Venus is not being avoided. Venus is being used. The proposal connected to Giuseppe Colombo treats the planet as part of the route itself. Instead of relying entirely on onboard propulsion, the spacecraft would pass through Venus's gravitational field and emerge on a different path. The sketch is elegant. That is also the problem. Elegant mathematics does not automatically become successful navigation. A line on paper can obey every equation and still fail to survive reality. The proposed route asks planners to trust geometry before experience. Why should Venus help reach Mercury? On the diagram, the answer begins to emerge. Venus is moving. Mercury is moving. The spacecraft is moving. The route is not a straight transfer between planets. It is a carefully timed interaction between multiple bodies already in motion. The meaning of the sketch changes. It is no longer an interesting calculation. It becomes a candidate mission. And once that happens, another pressure appears.
10, 9, 8,
The route enters evaluation.
we have liftoff.
Mission studies accumulate. Comparisons are made. Trajectory analyses grow thicker. Different possibilities are examined against the stubborn realities of fuel, timing, and mission objectives. The institutional cartographer's eye does not linger on personalities. It follows routes. One route after another is measured against constraints. Some possibilities become less attractive. Others become difficult to justify. The Venus-assisted trajectory remains. Not because certainty has arrived, because alternatives continue disappearing. That creates an unusual decision problem. Most engineering decisions can be tested repeatedly before commitment. Prototypes fail. Components are redesigned. Weaknesses are exposed before launch. This route cannot be fully validated that way. The final proof exists in the future. The only complete test is the mission itself. The planning documents begin to represent something larger than analysis. They represent commitment. Each approval narrows the space available for reversal. Each milestone reduces the freedom to redesign. The audience may expect that more study will eventually eliminate uncertainty. Instead, the opposite occurs. Commitment arrives before certainty. The proposal stops being an idea. It becomes a decision. And then a launch date approaches. The spacecraft leaves Earth in late 1973. At that moment, something important changes. The trajectory is no longer theoretical. It is physical. The route exists as an object moving through space. The line once drawn on paper is now represented by a spacecraft millions of miles from home. Options continue to disappear. No practical redesign can occur. No alternate route can be selected. No competing mission architecture can replace the chosen one. The spacecraft follows the path that was accepted months earlier. Its movement turns prediction into accountability. As Mariner 10 travels toward Venus, the pressure becomes visible through geometry. The encounter is approaching. The window is shrinking. The mission is moving toward the first real-world test of the idea. The spacecraft itself has become the experiment. Ahead lies Venus. And Venus now carries a responsibility no planet has carried before. The encounter arrives. From a distance, the event appears almost uneventful. There is no giant engine burn visible from Earth, no dramatic mechanical transformation. The important change occurs in motion. Gravity begins doing work. The spacecraft passes through the environment predicted by the calculations. Venus exerts its influence. The route bends. For years, the proposal existed as mathematics. Now reality has entered the conversation. The critical question is simple. Will the post-flyby trajectory match the prediction? If it does not, Mercury may remain beyond reach. If it does, an entirely new method of exploration gains credibility. The evidence appears in the spacecraft's path. After the encounter, Mariner 10 emerges on the trajectory planners hoped to achieve. The line on paper and the line in space begin to resemble each other. The shift in belief is subtle but profound. The mathematics no longer merely suggests a possibility. The mathematics appears correct. Venus changes meaning again. First, it was an obstacle. Then it became a tool. Now it becomes part of the propulsion solution itself. Mercury is no longer an abstract destination. It is reachable. The route continues inward. Eventually, the spacecraft reaches the planet that had seemed operationally inaccessible. Images arrive. Mercury's surface emerges from darkness and uncertainty. Craters, plains, and ancient terrain appear in the mission's cameras. The destination exists not as a calculation, but as observed reality. The trajectory provides something else as well. Because of the orbital relationships identified within the mission design, Mariner 10 achieves multiple encounters with Mercury rather than a single, brief visit. The consequences continue accumulating. What began as a route becomes a capability. What began as a prediction becomes a method. Later generations of planetary missions inherit the lesson. Gravity assists become part of exploration planning across the solar system. Spacecraft learn to borrow momentum from planets. Destinations once considered difficult become more accessible. The map changes. Not because engines suddenly become stronger, because navigation becomes smarter. And in the end, the story returns to the sketch. A hand-drawn line connecting Earth, Venus, and Mercury. At first, it represented possibility. Then it represented a proposal. Then a commitment. Then a test. By the time images of Mercury arrive, the drawing means something entirely different. It is no longer a prediction waiting for proof. It is proof. The safest-looking path had never been the path that reached Mercury. The route that succeeded was the one that asked planners to trust a future they could not fully verify.
The direct route to Mercury.
Reality followed the
Challenging for
equations,
early spacecraft.
and a single line on paper expanded humanity's map of the solar system.